So let's discuss the optimization or the settings adjustment. As you see here, these are the variables or the players to be adjusted. Now we come to the first setting to adjust, which is the steering. Steering of what? Steering of the Doppler scan line. And it should not be 90 degree to the flow direction. Why? Because 90 degree means cosine theta 90, it means that I'm having a zero Doppler shift. So the more oblique the angle theta, the better for the waveform. So let's have here some examples of steering of the scan line, Doppler scan line. In the first example here, example A, I'm having the vessel, it's almost horizontal. So whether I steer the line to the left or to the right, it doesn't make any difference because the angles here or there is the same. But if I'm having, for example, the vessel that is slanting to the left like this, so it's better to get the steering angle or the scanning line to steer to the left. So steering to the left because the vessel is diving to the left. If the vessel, for example, in example C here, the vessel is diving or slanting to the right, I can adjust the scan line in a steering angle to the right because I'm getting a better angle in this way. So now we come to the second adjustment, which is the angle correction arm or the cursor. And here, to know the value of the cursor and why I have to put it parallel to the vessel, because I want to provide the system with the angle theta, because other variables here are already provided. If you look at them, you see that they are already provided to the system. If I provide the angle theta, I can calculate or I can ask the machine to calculate the velocity correctly. So how can I provide the angle theta? If this is the way because I want to put the angle correction arm parallel to the flow. It means that I'm providing the angle theta to the system. Okay, so how can I do that? In the pulse wave Doppler spectral waveform, I can do that as I mentioned by the cursor or the angle correction arm. But in the dedicated CW, I cannot provide this to the system, but the system it depends on my adjustment of the probe to the skin, so that I can put the probe in a 60-degree angle to the skin, so that it can calculate as accurate the velocity range. Now, what if after steering of the Doppler line and adjusting the cursor to be parallel to the vessel wall, but still the angle is higher than 60? What is the solution then? Please do not deceive the system by putting or adjusting the angle 60 while it is not parallel to the vessel. Okay, how can we solve this problem? By what you call the heel toe maneuver. On the other hand, you can use this heel toe maneuver to make the cursor line or the angle correction arm parallel to the vessel while still keeping the angle 60. And here in this illustration, I put here the probe in two positions. The first position, which is the gray one, and this here shows you the angle is more than 60, for example here. Okay, but if I do the heel toe, like for example here, I'm pressing over the heel, what happened? The angle gets 60 or less than 60 probably by just simply rocking the transducer so that you get the angle still less than 60 and the angle correction arm parallel to the vessel. This is so vital to get an accurate measurement of the velocity. Here is an example of the cursor line adjusted parallel to the flow, which is parallel to the vessel. This picture here, or the pictures, are showing an example of why it's important to have the angle correction cursor exactly parallel to the vessel, and what will be the result if intentionally change the angle correction arm not in the proper direction. In pictures A, B, and C, this is the same vessel, the same flow, and the same Doppler angle, Doppler line. But the angle correction arm is misplaced in pictures A and C. So what happened here, if you look at the picture B, which is having the correct angle correction arm, if you look at the velocity measured, is what? 91.8 centimeter per second. Well, if you look pictures A and C, they are not correct. For example, in picture A, it is 15 centimeter per second. In picture C, it is 48.4 centimeter per second. Why is that? Look at the angle correction arms or the cursor. They are not parallel to the bezel. So the whole goal of these three pictures is to show what? Putting the angle correction arm parallel to the flow, parallel to the vessel wall, is a mandatory adjustment to get the proper or the correct velocity. If you misplace it or don't put it parallel to the flow, for sure you will not get the correct measurement. Somebody will say, okay, you keep telling 60 degrees, 60 degrees, 60 degrees. Why? 60 degrees or less, this is the best or the most accurate measurement. Because if I change the angle more than 60, the chances of mistakes are or the errors are higher than the chances of errors lower than angle 60. So this diagram here shows you these are the angles. So angle 20, 40, 60, and 70. You look at here, this is angle 60, and this is the curve. At this point, it starts to get shooting up. So here the range of error or the percentage of errors. At angle 60 or lower, the error is 20% or less. So I'm having the lower the angle, I'm getting less chances of error. But at the 60, this is a turning point. Why? Because after 60, you see the curve is getting shooting up, more almost vertical. What happens here? Any minor change in the angle, I'm getting more chances of error like 30, 32, just changing or just adding 10 degrees. So the message here is what? By 60 degree or less, I will get the least chances of error. More than 60 degree, I will get more chances of error. So now we come to the third player or the third setting adjustments in the pulse wave Doppler waveform. It's the sample volume or the gate. If you look at the sample volume or the gate, it has a big impact on the window and the systolic window in the Doppler waveform or the Doppler display. If you look at the window and you see some filling of the window or some broadening or the spectrum, look first for the gate. Is it correctly placed and correctly sized or not? So the sample volume position and size have some effect on the filling of the window or what you call spectral broadening. How is that? The position of the sample volume, is it central or peripheral? Central mean in the center of the flow, or is it in the peripheral near to the wall of the vessel? If it's central, okay, I will get most of the times, I will get a clear window. There's no filling of the window. But if it's peripheral, it might affect my window. It might bring some filling of the window or what you call spectral broadening. Also, the size, if we have a big size or a small size sample volume. A size which is a larger gate or larger size, sometimes people call it a longer gate, a long gate or a big gate or a large gate. It will bring some filling of the window. As we look at here in this this flow here, there's some tracing. If you look at this, this is the window here. This is the window. It has some filling, some flow here. Why? Because the big size sample volume is tracing big amount or big range of velocities. So you see here, slower velocities in the periphery and faster velocities in the center, both are traced, and that's why I get here some spectral broadening. But the opposite happens if I'm having a small sample volume. This is a small sample volume here. You look at the window here, it's very clear. Why? Because I'm having a small sample volume. So this is one of the reasons I might get some spectral broadening or filling of the window. One of the reasons is either positioning of the sample volume or the size of the sample volume. So now we come to the fourth setting to be adjusted, which is the scale. Scale is the PRF or the Doppler PRF, pulse repetition frequencies. This scale it should match the velocity that you are scanning. For example, if you are expecting to have higher velocities, the scale should be a little bit higher to match these velocities. If the velocity you are expecting to scan is a vein, for example, lower velocity, or you have, for example, you are scanning the vessels in a thyroid or a small part. Sometimes the velocities here are not that high, so then again you need to lower the scale. What is the reason here? I want to see the details of the velocity display. So this is the scale. What is in reality? What is the PRF? The PRF is determined within a range of the setting of the system. For example, you are scanning a shallow organ. You expect that you have the maximum range of PRF that you can adjust the scale with is a higher range. So you can have a higher scale here. But if you are having, for example, scanning the aorta or any deep organ, which is deeper to the transducer, the PRF will be lower. So you are limited in your scale. You can't get a higher scale in this range. Why? Because the maximum range of PRF to put the scale in is not that high. Now, the question is, what if I'm having the scale, I put it to the maximum, and then I have the velocity is much higher than this scale. What I will get then? I will get an artifact called aliasing. So now we come to some point about the aliasing and what is the reason here. The reason of aliasing is what? The PRF or the scale I'm setting to the machine, it has in the half of it is called the Nyquist limit. So a higher scale, it means that I will get a higher Nyquist limit. A lower scale, I will get a lower Nyquist limit. Why? Because the Nyquist limit is half of the PRF. So what does it mean to me? It means what? If I'm having a higher Nyquist limit, I have a higher range of Doppler shift that this system setting can accept without showing aliasing. So this is the Nyquist limit. Nyquist limit is what? Is half of the PRF. Okay? The highest range of the Nyquist limit, it means that I can accept higher velocities without aliasing. If I'm having a lower PRF and a lower Nyquist limit, and I will have in the opposite, I have a higher velocities, then aliasing will happen. Example here, if you have, for example, the PRF is 8 kilohertz, okay? So the Nyquist limit will be 4 kilohertz. 4 kilohertz means what? The Doppler shift beyond 4 kilohertz, it will not be shown correctly. It will have aliasing. So this is the limit of Doppler shift that the machine can accept or the ultrasound system can accept without showing artifact. So let's have some example here. If for a lower velocity, we know that we need to set the scale lower. If I'm having a higher velocity, I need to set the scale high. These pictures here, 3 pictures, are the same velocity, but 3 settings of the scale. This is the same velocity, but I set here the scale too high. What happened? The velocity shows, or the spectral waveform shows as if it's dwarf compared to this high velocity, to a high scale. If I'm setting the scale a little bit matching, so I lower the scale to match the velocity, now I get the velocity, the Doppler spectrum waveform is filling the whole scale without showing any aliasing. What if I'm lowering the scale too low? It's the same velocity here, the same arterial speed, the velocity here, but it shows here some aliasing. Why? Because I set the scale lower than the expected velocity of the arterial waveform here. So this is a chance to discuss aliasing here in this part, although aliasing will be discussed in more details in part 4. But let's have some point about aliasing here. So by definition, what is aliasing? It's misidentification of a Doppler frequency shift. Why? Because we have a lower scale. What will this result in what? This result in a display error. What does it mean, display error? The display of the velocity will be displayed in the opposite direction. This is the reason why I will get aliasing. The misidentification of the Doppler shift direction. The direction that is received by the system here is in the opposite direction, while it is truly it is forward, for example, but the system here identify it as in the opposite way. Why? Because the setting is not that high compared to the Doppler shift, which is a higher Doppler shift. Somebody might ask, so aliasing happens with the Doppler spectrum waveform? Yes, it happens there. And also it happens with the Doppler color. Color Doppler also shows aliasing. How about the continuous wave? Continuous wave Doppler? No, no aliasing. Why? Because the PRF is almost infinity. So the Nyquist limit is infinity. No way that the velocity can match this infinity PRF and Nyquist limit. And here, this is some diagram I thought that it might be helpful for us to understand this process or this phenomena of aliasing. This is the Doppler shift and this is the PRF or the scale. The PRF here, this height, this for example, it goes in kilohertz. Half of it will be the Nyquist limit. So Nyquist limit is the limit that this system with this PRF, the limit that it can display without aliasing. So this is the Nyquist limit here. Okay, what is this? This is the Doppler shift being received by the system. We know that is the FR minus FO, I will get the Doppler shift. Now Doppler shift is given to this phenomena here. Okay, what happens here? This part of the Doppler shift that is above the Nyquist limit will be aliasing, will be aliased here. This is the part that will be clipped off from the PRF, from the spectral waveform, and will show in the opposite direction. This part of the Doppler shift will not be aliased. So this is non-aliased Doppler shift, and this is the aliased Doppler shift. So in this diagram, what we can tell? We can tell that not the whole velocities will be shown in the opposite direction, only the velocities that are beyond the Nyquist limit of the PRF. So what is the reason now I can get aliasing now? Why is the reason I might get high Doppler shift higher than this, the setting here? If I'm having the operating frequency is high, we know that this is the formula here, okay? If this is at operating frequency high, I will get a higher Doppler shift. Higher Doppler shift, I might give it a chance to get aliasing here. So high operating frequency. What another reason? If I'm having a high blood velocity, of course, the velocity here, if I'm having a higher velocity, I will get a higher Doppler shift. I will get aliasing because it will be beyond the limit or the Nyquist limit. What else? If I'm having a high cosine theta, high cosine means what? If I'm having a lower angle like what? Close to the zero, for example, 20 or 25. So that's why sometimes if you have aliasing, if you get a chance to scan the same vessel or the same area from a different angle that is not that lower angle, it might help you to avoid the aliasing. But this is not actually practically, it's not a good chance for us. So the other reason is, what if I'm having a lower Nyquist limit? So again, I might have reasons to increase the Doppler shift. I will discuss this in the previous slide. Or reasons I might have a lower PRF. For example, like what? If I'm lowering the scale, okay, I'm not increasing the scale enough. So I need, in this condition, I need to increase the scale to avoid the aliasing. So what is the second reason? If I might have a deeper sample volume. Deeper sample volume, like you're scanning the aorta, not scanning, for example, the carotid. Carotid, they are close to the skin, so they are the PRF will be a high PRF. But if you're scanning for example, the aorta, okay, and you get the chance to get sample volume at the aorta, what happens here? The depth of the sample volume is much higher than the depth for the CCA. What is the end result? I might get here some aliasing. Why? Because the PRF is lower. I'm getting a lower PRF, lower Nyquist limit. I will get aliasing. So now we have some discussion about how can I avoid aliasing. I have aliasing, how can I avoid or how to eliminate. First option is to increasing the scale. Increasing the scale, increase the PRF, you'll increase the Nyquist limit to avoid aliasing. What if still doing this, but still there is some aliasing in the image? What can I do? Select the lower frequency part of the probe or get a probe with a lower frequency. So in this condition, what happened? A lower frequency probe, you get a lower Doppler shift, and again, you can avoid the aliasing. If these two didn't solve the problem completely, what you need to do? Try to select another window that you will get a shallower sample volume, not a deeper sample volume for the same area. Actually, this is not so practical, in my opinion, that because most of the time when you scan, by the default, you choose the sample volume with the shallowest position for the probe, or you choose the probe that is closer window for the vessel. You are not scanning the vessel from a distance. So this is one theoretical, yes, but not practical. These two are the two practical points. What if this didn't help? I believe that if you use the continuous Doppler, continuous wave Doppler, this is the solution for this situation. Many machines that we have the integrated CW Doppler within the array transducer. So you can use this option. It helps avoiding the aliasing. Okay, and the last thing, which is not welcome much by many of the authors, is to perform a baseline shift, lower the baseline. So the fifth setting to adjust is the Doppler gain. Doppler gain, it affects the gray scale or the gray shade of the spectral waveform. So if you look at here, this is actually what you call the z-axis of the display, the brightness of the spectral waveform. I should have it not too much bright, not too much dark. So a medium gray shade is accepted. But what if I'm putting a higher gain? What happened? There are some drawbacks here. Number one, the background will show some artifact. We call it some noise artifact at the background. It looks like as we're having raining here. Okay. The second drawback is I might get some false elevation of the peak systolic velocity here. If I said that the proper gain, probably one of these lines here that shows peak systolic velocity, they are not true peak systolic velocity. So I might have false increase in the peak systolic velocity in the measurement. The third one, which is I might get some false spectral broadening also with the Doppler gain set too high. So this is the reason why we better have the Doppler gain set in the proper adjustment, not to have the background artifact, not to have false measurement of the peak systolic velocity, and not to have false spectral broadening. Number 6, we have what we call the wall filter. Wall filter is recommended to remove some of the lower Doppler shift that are displayed near to the baseline. Okay, they might represent sometimes the clatter that is shown near to the baseline, but be careful here because as the way you are removing the clatter by the wall filter, you might also remove some useful information, which is, for example, if in this picture here I have three settings of the wall filter at the same display, but I have three settings. What happens here? Okay, this is I put no filter here. I put here some medium filter wall filter, you see here it starts to remove parts of the waveform. Okay, if you put higher wall filter, what happened? I removed completely the diastolic flow that is here. So be careful about putting the wall filter. It might be harmful, not beneficial. The last setting is for inversion. Inversion actually is sometimes you need it if the flow is supposed to be forward flow, but you put the probe in the opposite direction, or you put the steering of the angle, the Doppler line, you put it in the opposite direction. So what happened? It shows below the baseline, like here. So there is here some inversion of the waves because of the incorrect interrogation of the direction of flow. So in this condition, what I need, okay, I need to put inversion, and the inversion will put the forward flow back on the top of the scan line. Okay, if you need it, you can do it. It doesn't harm anything about the measurements. You can get the pixel velocity and everything correctly. So there is nothing wrong with this one. Now, before I leave this is the last setting. Now I need to have some way to summarize what we have the settings adjustments here. If you look at the Doppler spectral waveform, we have an anatomy, you have the spectral waveform down there. These are the settings that you need to do. In the anatomy, you have if you apply the spectral waveform, what we have, the pulse wave, you will get a Doppler line, you get a sample volume, you can get a cursor. These are the three things that you need to adjust. You need to adjust the steering of the Doppler line. You need to adjust the sample volume or the gate. Is it the correct size and correct position? And you need to adjust the cursor. It should be parallel to the flow, and still it has an angle of 60 degrees. So these are three settings. The last two settings, you will find them down in the display. You need to adjust the gain, okay, and you need to adjust the scale. Both are another two more adjustment that or two more adjustment that you need to put in the pulse waveform.